Good afternoon, everyone, and welcome to the EOL seminar series. It is my pleasure to welcome Dr. Zhaoxia Pu, who is a professor of atmospheric sciences at the University of Utah. But before joining the university, she was a postdoc at the NOAA NCEP Environmental Modeling Center and a research scientist at NASA Goddard Space Flight Center. Dr. Pu is a busy scientist. She is involved in NOAA's Hurricane Forecasting Improvement Program, Next Generation Global Prediction System, and Unified Forecasting System programs. Her research focuses on satellite and radar data assimilation, high-impact weather systems and extremes, land-atmosphere interaction, and atmospheric boundary layers over complex terrain. Zhaoxia is a fellow of the American Meteorological Society and Royal Meteorological Society, and she is a member of the NOAA Science Advisory Board. She is currently an editor of the journals, plural journals, Weather and Forecasting and the Journal of Meteorological Research. She has led and participated in numerous field projects, one of which is the NSF-funded CFACT project, which stands for Cold Fog Amongst Complex Terrain, which we at EOL supported. And Dr. Pu is the PI for CFACT. In her seminar, Zhaoxia will be talking about observations and modeling of cold fog using CFACT observations collected last winter. For those of you watching online, we are answering questions that you can type via Slido at the bottom of your presentation screen, and we will save your questions at the end of the seminar. Dr. Zhaoxia Pu, welcome to NCAR, and the stage is yours.
Thank you. Thank you, Jackie, for the introduction. Good afternoon, everyone. Welcome to my seminar. Thank you, and it's a pleasure to be here today to talk about the project I work with NCAR EOL. First of all, I would like to acknowledge all the CFACT, co-PI, co-IS, and also all the students and early career scientists who participate in the program, especially to thanks to the NCAR EOL, ISS, and ISF teams for their support. For the talk today, I'm going to introduce the science background, the objectives, and the research theme for the CFACT, and also talk about the field campaign deployment, observations, and also showing you some of initial results with numerical simulation and the prediction of the fog. And lastly, to address some of the ongoing and the future work. So first question is, what is a CFACT? So CFACT is an NSF-funded field campaign and a science project that investigates cold fog formation in mountain valleys. So our field project was conducted at the Heber Valley, Utah. So Heber Valley, Utah is 45 miles east of the Salt Lake City. So it is a small valley, and I will talk about this later on. And we have 6 weeks field project conducted in January and February 2022. And so the NSF NOAA Atmosphere Observation Facility provided support through the NCAR EOL and the University of Utah, and also the Environmental Canada and the private company support this project with additional instruments. So I will show you some of the example later on. And we have very ambitious science goal because we have good team here. So this is our CFACT science investigator, and include myself as a modeler, and also Eric Padiak as our observation and theoretical scientist on the dynamics and the boundary layer. And Dr. Ishmael Guptepe was a well-known scientist in fog-related microphysics modeling. And he was employed by Environmental Canada and currently moved to Montreal Technology University My colleague Gannett Hanner and Sebastian Hawk, and both are observational scientists in many of these aerosol and air quality related instrumentation and data analysis. We also have Dr. Jeff Anderson collaborate with us for the modeling and the data assimilation issue. So we have really good science team and with NCAR support. So this is very nice project. So first thing is why we study fog, and so we choose it as our subject. So fog is high impact weather event. So it is the second most common cause of the weather-related aviation accident behind the storm wind. So in United States, between 1995 to the 2004, more than 10,000 people were reported to have been killed in a fog-related accident. So which means it's still a very severe weather to be concerned. So regarding to the cold fog, is a fog occurring at temperature below the freezing point. So this is different from the warm fog or marine fog we commonly see. So however, in the west of United States, this, the fog form in the complex terrain and at high elevation. So it happens as frequency comparable to the marine fog. So it is frequently happened, but very poorly understood and difficult to forecast. So the reason of this difficult forecasting is this fog among the complex terrain usually have high variability. So if we compare the fog average, the annual hour of the fog in northern Utah, you can see there are strong variability from valley to valley. So it's very large variability. And also we have lack of observation. So current weather observation system cannot capture fog. And a common methodology to forecast the fog for one valley cannot apply to the other one. So there is strong uncertainty in the numerical model and the forecast environment. Lastly, so it's very lack of the study because most of our field project conducted emphasize warm fog and sorry. So most of the fog experiment we have seen emphasize on the warm fog condition, and most experiment taken place along the California coast. There are lack of the emphasis on fog with over the mountainous terrain. So some of the project conducted in Europe, Europe, but they're still emphasize more on the radiation fog rather than complex terrain influence. During the DOE support the project, which is a mountain, study the mountainous flow methane project. We had a pilot field project over the Heber Valley, but we only have sounding observation and microphysics observation. We do not have fully support of the ground-based observation during the time. So that's motivated us to study this cold fog over complex terrain and have this field project. So scientifically, there are also complicated issues related to the cold fog. So first thing is cold fog has the process involves radiation, energy exchange, turbulence, microphysics. So the fog-water balance has a strong interaction with all these different components. Specifically for the complex terrain regarding to the fog, which involves boundary layer processes and also fog modulated by the topography and the radiative effect. So which is largely we found during our Met-home projector, so even the gravity wave and this thermal-driven flow and all of these things plays a role, modulate the fog formation during the complex terrain. So really, there is needs for the dense network to understand this. Regarding to the numeric simulation and forecast, we already said that the fog forecasts are very challenging. So there are very few studies of cold fog condition in mountainous region. And most of the ice nucleation parameterization are developed for cloud, not for the fog. So even the fog is a cloud near the ground, but it involves much different processes. NWP usually fails in forecasting the fog and its intensity. So the review paper done by Gupet et al. Say that the visibility prediction bias can be as high as 100%. So during the Met-home fog project, we performed a real-time wolf forecasting, and so seems like the fog was successful for several cases in Salt Lake City, but missed all the cold fog over the Heber Valley because the cold fog processes are much more complicated. In the Salt Lake Valley, we see more fog associated with persistent inversion. And as far as for the NWP concern, we know the NWP has a boundary and the initial condition input into the numeric model, which include the dynamic and the physics processes. So in terms of the fog prediction, we see the errors from the initial boundary condition and also the physics parameterization. So it's quite severe. In the NWP model, we see a lot of these uncertainties. So I can show you the example. We're running with the cloud permitting scale WRF forecast during the Met-home fog 2015. So we're seeing that the very serious error if we compare the WRF simulation with the ISOS observation, you can see the large biases in the near surface atmospheric condition regarding to the temperature and the moisture and also the wind field. So more seriously, if we compare with the Tedderson balloon, which sample the near surface temperature and the relative humidity, you can see there are large discrepancies. The temperature error can be around like 10 degrees Celsius, and the relative humidity can be very large differences. So because in the Heber Valley, in the mountainous fog, so oftentimes we see a formal fog which is very shallow. It's maybe just like the height of the tree level. So then this large error will be given almost impossible to forecast the fog with a numerical model. So those are the things we concern, and we want to use the newest technology in the CFACT to gain new knowledge and also improve the numerical modeling and the prediction to study the cold fog. So therefore, the objective for the CFACT set in the three emphases. So the first one is to investigate the cold fog development and the environmental condition in complex terrain with latest observation technology through a field campaign. So we propose the field project. And then the second one is improve the physics parameterization and the visibility algorithm, use a numeric weather prediction model, and then lastly, to develop data assimilation and analysis methods for current and the next generation NWP models. So this is very ambitious goal, so we just specify these three as all these objectives. You can see we try to understand the multi-scale processes which related to the fog formation, include the synoptical, mesoscale, macroscale, and also the thermal-driven, and also the impact of the aerosol and the physics processes, and also the surface process, snow on the ground, and all of these components with data analysis and modeling study. Our final goal certainly is to validate and improve the physics parameterization and develop data assimilation method for the NWP model to achieve the better prediction. So this is pretty ambitious goal, and so we begin with a field project. Compared with this field project we have in the past, so we expect the CFACT enhance the fog study opportunity by adding the aerosol impacts. So we have aerosol measurements and also expanded the physics, microphysics measurements with NCAR ISFS support to get the more wide observations. I will show some example later on. And also we propose to have more modeling study, and the satellite remote sensing and the data assimilation will be included. So CFACT really set the ambitious goals to get all this useful observation, and also to get into the next generation model, so which is sub-kilometer scale model. So first thing is for the field project in the last winter, this is our observation network. So as you can see, the Heber Valley is a very narrow valley, has about 16 kilometer diagram. So it's a very, the distance between here to here is about 16 kilometers. So it's very small valley, but it has a valley basin and also mountain, and also have the reservoir and with water body. So it's represent the typical mountain valley around the world. So with the setup of the network, we have two super sites. So one is near the Deer Creek Reservoir, which is water body, and this is also beneath the place has most of the fog occurrence. So you can see we set more network here. I will show you the details. And then we have another super site, which is in the north here, which is intended to capture on this drainage flow and the flow colliding from the different these mountains. We also have 9 satellite sites set for the typical representative location, and another 8 no-cost meteorological station, so which is green dot, and this satellite site marked by red dot, so managed by NCAR. So you can see we set this dense network as far as this Deer Creek super site. So we have this aerosol trainer and also sounding site, and specifically, most importantly, set this NCAR 32-meter towers to measure the turbulence in the boundary layer and also the fluxes. And also we have this 3-meter turbulence tower set on the this Deer Creek super site. So there is a LiDAR station, and also other PI instruments are all set in the Deer Creek super site. And in terms of the satellite site, so we have mainly these 3-meter towers with many of these instruments, and then many of the EOL people may be familiar with this. And so the deployment certainly, so there are variety of the instruments, and here is Steve, and also Jackie is visit the site, and so yeah, we have some picture, nice picture here, and it's fun, and just ISS distribute this to the 3 field sites. Some of the instruments, Bill is here to manager and oversight all these sites to operate continuously, and we really appreciate NCAR. So during this very cold season, and they operate all these instruments during the whole period continuously and offer really useful data sets. And this is University of Utah aerosol trainer and the Gannett Harners group managed to have this aerosol particle size and also the spectrometer operator. And they also have this aerometrics mini-vol, which is filter samples that measures aerosol during the fog development. And another thing to highlight is Dr. Ishma Gutepi provide a suite of this macrophysics instruments, and so we build up the macrophysics station over the DC Hooper site, and which is very useful to capture some of the macrophysics properties. And so overall, for the CFACT instrumentation, we capture this turbulence, thermodynamics, macrophysics, radiation, energy exchange, and aerosol, and with all kinds of instrumentation. During the field, our daily operation and planning meeting was held every day, and so during the meeting, we review the status of instrumentation and check if everything's work. And also we do the weather briefing and the discussion and the plan for the LPs, and make the go, no-go decision, and also some science debriefing. So it's fun to have the students, scientists, and also the NCAR people all together. And so yeah, it's great experience, and we have a lot of discussion. So to help understand the field data and also talk about the science. CFACT also provide the education and the outreach activity. So here is Bill conducted this radio sound launch training to the students. And I think that you can see that how enjoy students actually in the field. And also we have our class, instrumentation class visit the site, and so they have the real time to learn how the field and the measurements will be taken, and the students got good experience. And we have greater than 20 graduate students and undergraduate students participate in the field observation and also help on the field, and they all very pleased to have this experience, and they are great helper. So during this 7-week field deployment and also the field work, we conducted 9 ALPs. Because of the Western United States drought condition during the time of the field. So we see a lot of time we have West Coast blocking high stay. So therefore, in the Heber Valley did not really get enough water vapor supply from the large background. And you can see from US drought monitor and during our field, so Utah is experienced this drought condition. And also due to the very cold temperature, reservoir was freezing, and it's prevent the local water source supply. And we did not get enough snow in January right after our field project start. So then the snow was melting at the beginning, and so then we did not see much snow on ground. This prevents the fog condition. So then among these 9 LPs, we only see fog in the three events in our planned LP, but we see other 2 fog events in the nearby valley, not in our observed site, but in a nearby valley. But in the end of the field, we have seen another 2 fog events, and fortunately, we still have part of the instruments still operate, so we capture partly sampled them, and we appreciate NCAR for the Steve specifically proved to have last day extended for us to have a complete sampling of the very important ice fog event, so which is very essential for our field project. So even we did not get really full spectrum of the fog event during the LP, but we collect very useful data because among all these LPs, since we carefully planned and so the NCAR keeps the normal operation, so we captured this nighttime inversion on the stable boundary layer. We also have some of the fog happens in the nearby valley, provide us with fog versus non-fog in terms of large scale and mesoscale condition, which helpful for the us to study the fog formation. We also see the ice crystal formation during the LP and also sampling the moisture advection and the transport in the Heber Valley. All of these, even it's not the fog condition, but all of these conditions are very essential for the fog formation. So the data is still very valuable to study the cold fog. So we feel like this is still very, very successful observation and field campaign. So even we do not have all the fog LP, but we got some fog and non-fog and with important condition for the fog formation. So I think the data sets are all valuable. So just showing you some of the example about what we get from the observation. I will particularly showing the LP8. So in this case, we have several intermediate period of the fog during the 5-hour period. So this is NOAA ABA brightness temperature. So as you can see here, so over the Heber Valley, so you can see some of the scattering patch fog event happens here, the patch cloud or the fog. So this is one of the since the University of the Wisconsin seems they specifically provide us data during the field campaign, so which is very valuable observation from the satellite. And so NCAR EOL ISF observation for this LP, you can see the visibility and also 2-meter relative humidity. So this is relative humidity with respect to ice. You can see some over 100%, which is saturation, represent the fog condition. And also the temperature drop during the fog formation well captured, and the wind speed, so NOAA wind speed showing in the place we have the fog. So I want to note here is, as I said, the Heber Valley is a very small scale valley. So you can see how the NCAR data make the nice differentiation between these stations. So those stations are close by each other, but you can see how much differences of this condition changes. So this is very important because this network in this small scale give us not only the valuable data to understand the variation in the valley, but also offers data for us to validate our model in very fine scale. So this has a lot of meaning. I will show you in the model part for this as well. Okay, so this is a radial sum profile. So for each LP, we launched the radial sum for 8 times. And for this particular case, you can see the radial sum captured the cold pool development and also the inversion during the fog formation, and also the change of this the mixing ratio profile during the fog. And so you can also clearly see in the warm temperature and the dry air will make the end of the fog event. So this is very useful data sets to understand the boundary layer processes involves fog and fog formation. And regarding to the microphysics, as I said, so this instrument provided by the University of Utah and also by the company we have involved and also the Environment Canada, you can see we get very valuable ice crystal number of concentration and also ice water content and also this so-called size distribution. So this black line marks the fog period. So you can see it's clearly captured the fog event, and also this CDMS instrument also give us some clear indication about the fog occurrence during these 5-hour events. And then also this aerosol size distribution. So as you can see from Gannett Haller's measurements, you can see in the fog, during the fog period, you can see the decrease of this aerosol. So you can see in the change here and here indicates the fog. It's actually corresponding with the fog events very well. And this is the first time we measure the aerosol during the fog. And so definitely this is very important data sets. So regarding to the numerical prediction, so during the field campaign, so we conducted a real-time wolf forecasting with a multi-scale setting. So in addition to the 1 kilometer, which is cloud permitting scale and close to the current operational, so we running for the 400 meter resolution. So as you can see here, so this is 1 kilometer resolution, so represents the Heber Valley. We cannot see the details, but with the 400 meter wolf simulation, we can clearly see in the temperature and also the flow structure over the Heber Valley. So I'd like to mark here, so during the field campaign we had in the year 2015, we only have cloud permitting scale simulation. So as we marked, so we missed nearly all the fog events. But this time, so even we still hard to predict the fog because it is challenging, but at least our model performance give us a very reasonable local flow and also the temperature variation forecast. So as you can see here as an example, so we see the 2 meter temperature, 10 meter wind, and also the relative humidity from the different satellite sites. So you can see with the 400 meter resolution, wolf model is capable to just differentiate all the difference between the different stations, and also compare with the radio sound observation. So the main feature in the boundary layers was well captured. So I think this is very important to say the wolf model with a high resolution sub-kilometer is valuable for the study of mountain flow. Definitely, so if I compare with this figure and the previous observations, so we can still see model has large bias, which means we still have room for the model improvement or data simulation. But at least, so this 400 meter resolution seems to be promising. Another point needed to make here is, so in order to capture this cold fog over mountainous terrain, we needed to run a large eddy simulation. So that's so then in the CFACT, we emphasize our modeling study in the sub-kilometer. So currently at NCAR PMC, the operational model running for the few kilometer resolution, so which is in the cloud permitting scale. And so in the future, with computer power increase, so we may see the sub-kilometer as a next generation model. So I think we move forward for this direction with a field project. So this is a 40-meter resolution simulation for the flow and the temperature over the near surface temperature over the Heber Valley. So you can see in how successful the 40-meter can actually perform. So our model simulation emphasize on the multiple scale because we do the nested domain to capture the synoptical mesoscale and the large eddy simulation. All these scale included. And in terms of the model validation and the improvement, we will emphasize more on the physics parameterization improvement. We see with the model validation and the sensitivity study, and also with large eddy simulation, how much we can do. And I think it's quite promising from the data we get. And we are also going to develop this fine scale data simulation and to further study the predictability. So post-field study seems to be very ambitious, but I think the data will be available, and we will call for community collaboration to use this data. I want to show you the example about the large eddy simulation we have done so far to examine the turbulence effect on the fog formation. So this is a study my postdoc Xin Li and me we have done during the CFACT field project when we prepare for the real-time forecast. So we did it for one of the Meton case in the year 2015 to begin with. So we use 5 nested domain, so you can see we have 25, 5, and 1 kilometer, and 200 meter, and 40 meter resolution to run the WRF model in the multi-scale. And so as you can see, from the model validation, if compared with her analysis of the liquid water content, so which indicates the patch fog over the Heber Valley. So you can see the resolution from the 25, 5, and then 1 kilometer all missed the fog. So only large eddy scale, so with 200 meter and 40 meter resolution, so we captured the fog event. So this is 200 meter showing the liquid water content, and so this very small one is a 40 meter domain. It's very small. And also we compared with the sounding, so you can see the conclusion here is this large eddy simulation really makes the model simulation fit to the observation much better than the other scale. And in particular, we see the turbulence evolution during the use of this 40 meter LES or 200, even 200 meter have some representation of the turbulence. So this is momentum flux from the 1 kilometer, and this is from the LES, and also the heat flux. You can see this 40 meter really showing the strong turbulence in LES. So one thing I want to note is here is really this time series showing you how the turbulence plays a role for the fog formation. So what we see here is this fog starts with here near the mountain when near the evening time, so when the temperature drops and gets some saturation happens, and so the fog form, and then through the advection, so it went to the valley, but the ground we cannot see the fog for the few hours until when you have seen this turbulence actually plays a role to bring this. So this, what we put down to the valley, we can see the fog. So you can see in the really not only the advection, by advection itself, we cannot see the fog. It is the turbulence mixing plays a role even in this stable boundary layer to help the fog formation. So we calculated this liquid water content tendency, and through the contribution from the advection, turbulence, and also the macrophysics, you can see the macrophysics, and so this liquid water content really plays a role for this valley fog. So through this line, this is the DC supersite we currently seeing. And so you can see in this is definitely the role of the turbulence effect for the fog formation. So then with the CFACT case, we looked at the LP6. During the LP6, we see the 2-hour continuous fog in the DC site. And so this is a large scale synoptical we see in the high pressure, clear sky, common wind. This is usually the common case. We will expect the fog possibly form. And also, so from sounding, we see the inversion and the saturation. So this is indication of the fog formation. And from this macrophysics and LiDAR instrument, we also can observe the fog. And the temperature drop and also saturation, as I noted. So this is local condition, which usually helps the fog formation. So this are we all seeing from the observations we get. And also, this is very localized fog. So you can see from the NCAR measurements. So that's why I say that these observations are very valuable, because from different sites, you can clearly see there are, even this is very small valley, part of the valley has fog, and part of valley, we do not see fog. So the reason of this is the 2-meter humidity really tells the story. Okay, so we did with this wolf simulation, and so with this, so this 40-meter resolution simulation and 1 kilometer resolution simulation, and you see 2-meter temperature, 10-meter wind, and also liquid water content. So you can see in the 1 kilometer, you do not get this fog. And because liquid water content is all zeroed out. But with 40-meter resolution, definitely you can see in this liquid water content behavior. Although in this case, the fog was over-predicted because our model produced longer period of fog, but we still see the fog from this large eddy simulation, but we do not see fog from 1 kilometer resolution. And in terms of the turbulence evolution during this CFACT LP6, so this is NCAR tower data from the high resolution observation. So we calculated the turbulence from the different height. So this is 2 meter, and the radar showing the fog period. So this is zonar turbulence, and this is meridional, and this is vertical, this is TKE, and also the same thing for the 32 meter height. So you can see in the turbulence definitely is there before the fog formation, so it's relatively high, but during the fog form, so during the fog evolution, it's getting lower, but when the fog dissipates, it's getting high again. So definitely seeing the role played by the turbulence. And yeah, so appreciate to have this observation because it proves the role of the turbulence during the fog formation evolution. And if we calculate this temperature tendency from the advection and the turbulence, and also look at the temperature and the liquid water content, so you can see this variation also tells the story for this particular case. Both advection and the turbulence plays a role, and it proves what observation said here. We are still in the process to validate further for this model simulation, but at least this observation already offers us the ability or capability we can further explore the science question and understand the fog formation processes. So just to summarize, so this CFACT is a field campaign and also the science project which we dedicate to the observations, modeling, and the prediction of the cold fog. And we intended to investigate cold fog develop and the environment condition, use a field campaign, and we collect the useful data. And for the postal field research, so we intended to improve the physics parameterization and also the visibility algorithm used in the numeric weather prediction model, because we're seeing a lot of these uncertainties in the model. And also lastly, because of the data available, we want to develop data assimilation and analysis method for current and the next generation NWP model. So I'd like to highlight the next generation model we want to emphasize here is sub-kilometer, because sub-kilometer scale simulation and prediction definitely is necessary for the fog prediction over complex terrain. So CFACT field campaign collect unprecedented data set for improved understanding of cold fog, stable boundary layer, and mountain weather. So as I said, so because of this dryness and the drought over the western United States, we did not get the full fog LPs, but we collect useful data sets for the NWP validation for the mountain weather prediction. So it's still considered a very successful campaign. And so then we needed to, we are now work on the comprehensive data analysis, data assimilation, modeling, and also verification, validation, and the predictability study to follow the field campaign. So ultimately, our research moved towards the improved cloud permitting scale and the sub-kilometer scale numeric weather prediction. So as I said, so we have a student postdoc support our field, and also we get large community support from the Salt Lake City air quality and also the meteorological research, and also we get support around the world for this campaign, and they contribute ideas and also the expertise to us for the very valuable discussion. So of course, so NCAR EOL provided this data archive and the field catalog, so you can check our field activity and also the data availability and all those things. So all the data from the NCAR, most of them are available already to the community. So as I said, we set this very ambitious science goal, but with our team efforts, we still will see our limited efforts, but so I think with the community involvement and the people use our data, so we will eventually achieve this goal very well. So I think this is my talk. I thank you for your attention and happy to answer questions.
Well, thank you, Zhaoxia. That was a really great talk. It's wonderful seeing how EOL data is being used. It's very gratifying to see us to work with modelers to see that our observations are being used to help improve forecasting and prediction skill. We have time for questions. Does anyone have a question for Dr. Pu? Bill.
Thank you for that great talk. So what kinds of measurements do you wish you could have had at this campaign that we didn't actually take?
So you mean what kind of measurements I wish?
Yeah, would have helped that we couldn't take.
Yeah, I think the most valuable data sets so far we have is near surface, which is we most needed measurements. So in the meantime, so if we would have I think there are something a little bit higher than 32 meter tower. And yeah, if we have the more boundary name measurements and more dense networks, that will be very useful. Because a lot of time we cannot put our model, the first level, very low. And so then I think there is something higher than that will be even helpful.
Any other questions?
So Chris.
Hi, Zhaoxia. So you showed some results where you were comparing to the HER in one slide.
Yeah.
I wondered, could you say a little bit about what you think the state of the art for, say, the HER for NWP in the Heber Valley is? How good or bad is it?
Yeah, I think that's a very good question. And yeah, because when I give talk, other people also ask. So first of all, I want to clarify her here is analysis, which is not a forecast. So I'm not sure if by the forecaster, if her can do better than LES. But definitely, I think her analysis is the best regional analysis and the fine resolution analysis we can get now. And it's definitely showing this liquid water content very well. So yeah, it represents a good analysis, but not the forecast.
So your sense is that there's actually, it's the observations that are making
Right.
that analysis good and not...
Yeah, that's good point. Yes.
Short-range forecast is not very good.
Yeah, the short-range forecast, I doubt, because we're seeing from WRF 1 kilometer resolution. Yeah, we did not get anything for here. Yeah.
We have a question online, so we go back and forth. We have a question from Ian Cornejo, and this person says, is there evidence of latent heat release from fog formation driving convection in the boundary layer? If so, what is the feedback of latent heat release and convection on the vertical extent of cold fog?
Okay, yeah, this is very good question. I think I would say yes, if this fog happens in the warm region, I will immediately say yes, the latent heating plays a role. But since this is cold fog, and also this happens in the stable boundary layer, so that's some question I think definitely I need an answer after we do more observational and modeling study to answer. So I think the answer here is I cannot answer this question exactly now, but this is good question to look from our data and the model simulation.
Thank you. You had a question?
Not knowing much about fog, but you said that the turbulence, or quoting that, LES generates better, strong turbulence mixing in LES helps the fog formation.
Yeah.
Could you just elaborate on that a little bit?
I think here is because of the turbulence effect, which actually helps the mixing of this microphysics property, like here the liquid water content. Yeah, because of the turbulence mixing effect, it's eventually arrives to the ground.
We have a question. We have a question from you.
Hi, Professor Pu. Thank you for your talk. I have a question related to you showing that you are advocating that going to higher resolution sub-kilometer or LES that promotes showing improved forecast for fog. So I have a question about how do you think is that increasing resolution contributing to this? Is it because it's better resolving the topography, or is it because increasing the resolution that you can have this, where you show the observation even in a very small valley, that they have a variation spatially, so you have a very fine resolution that have a better, closer location to the site, where it's contributing to your improved simulation?
Okay, I think this is a good question, and all you said I should say yes. So because of the high resolution, we better resolve the processes and also better resolve the terrain effect. That is true, and also I think when we run in this large eddy simulation, we directly use TKE instead of use parameterized physics. So that also helps because you can see from the 1 kilometer we use parameterized physics, we cannot actually get the fog. The fog was failed to produce. But with the TKE in a large eddy simulation, so we can get this. So this is one area we would move forward and to see what we can do with improved boundary-based parameterization to get the fog be predicted by the 1 kilometer. So that's something definitely we want to move forward. Thank you.
Hi, Zhaoxia. Thank you for the nice talk. I just wondering, I know WRF has a fog parameterization scheme. Have you ever played with that? I know explicitly probably hard to predict anything like fog at a kilometer or 3 kilometer, but there is a fog parameterization scheme in there. I wonder if you
Okay,
played with it.
I will. Yeah, thank you for reminding that. I will have a check. So the one thing I tried, so because I didn't mention for the real-time world forecast, I did not use this LES setup. What I used, you have a gray zone parameterization, and I use that one. So that one seems works as well.
This is just for fog parameterization.
So there is one, yeah,
There
for
is a
fog
fog
particularly.
parameterization.
Okay, I will try that one.
Yeah, I was just wondering if I don't know how well it
So then,
performs, but
is that available in the current version? It's been there for a while. Oh, for a while. So it's a microphysics scheme or?
no, it's I think it's you can find it in the boundary layer.
Boundary layer.
Yeah, it's part of the boundary layer physics, I think. Yeah.
Okay, so I will check, but one thing, yeah, just to be caution is, so that's for the warm fog or cold fog.
Right.
That's some concern there. Yeah. I think I would like to look at that. Thank you.
I think there's time to have some collaborations tomorrow with some of the M-Cubed colleagues to talk about that.
Right.
Right. Do we have any further questions from the audience, from Slido, from online? No. So just one final comment. So because it was winter that we were doing this experiment, ISFS set up early. We actually set up sort of at the end of November. So we have provided data that is not just for the January, February timeframe of the official campaign, but also includes December. And my understanding was that there were some significant fog events that occurred in December. So do you plan to look at that data?
Yeah, definitely. So because given the meteorological condition, NCAR data provided, we definitely will look at. But the only thing is, with that data sets, we miss some of the macrophysics and other measurements. But I think it's still valuable data sets, especially for NWP validation purpose. Yeah.
At least certainly look at the temperature, relative humidity, and wind speed.
Right.
So you have those basic measurements.
Yeah, I think those are very nice. Yeah, and yeah.
If we have no further questions, thank you, Dr. Pu, for giving a seminar. Let's thank our speaker.
Okay, thank you. Thank you for coming.